Hello, everyone. We are very happy to have Zhenbin Young today. And Zhenbin will talk about firewalls from wormholes. So, okay, so please start.
Okay, thank you. Thank you so much for the invitation. It's a great honor to visit Tata Institute virtually. I hope one day I can visit in person. Today I'm going to talk about a recent work in collaboration with Doug Stanford. Our paper have published in Archive last month. It's about typical state firewall paradox. So I'm currently at Stanford University, and I'm going to join Tsinghua University next year at the ISTU. So just a brief introduction about myself. Okay. The problem we want to address is the typical state firewall paradox. Of course, there are a lot of versions of different typical state firewall paradox, but just to give you a brief history or background of what people have argued about whether typical state have a firewall. So by typical state, we mean if we consider black hole in with some energy parameters, and in that macroeconomic ensemble, and if we draw a random state, one can ask that state have a typical have a firewall that we call a typical state. For example, in this AMPS paper, they argue that in typical state, the typical state of black holes should have firewall. The argument is quite simple, so let me briefly review here. Let's consider status with a stationary black hole. So, for example, a black hole from forming a dust of matter and fall to equilibrium. Then we have the Hawking modes near the horizon. We call it the exterior mode as B and the interior mode as B tilde. So if the horizon is smooth, then the state, we call it psi, should be in this special entangled state, like EPR type of states in B and B tilde. So the capital B tilde B is a ground state. And then smoothness of horizon requires this specific type of entanglement structure between B tilde and B. Then one can consider the number operator of B. The number operator is approximately commute with the Hamiltonian. And then one can consider applying this unitary operator U of theta, which is like rotating the B particle by phase theta. Then this little rotation will break this entanglement pattern and therefore break the entanglement structure at the horizon. And since number operator almost commute with Hamiltonian, acting on this U of theta, still bring a state inside of the same energy window. So U theta of psi, it will become a firewall. And one can consider the many different angles at many different species of B, and that AMPS argue that start from a smooth state by acting on these different U's, U thetas, we can create a lot of states, and they all have firewalls. And their conclusion is almost all states should have firewall, and therefore typical states should have firewall.
Sorry, Zhenbin, I'm sorry to interrupt you here. May I ask a question, please?
Yeah, please. Yeah.
I should know their argument better, but are you saying basically that this number operator will commute? Let's do an example where we just have the Minkowski state, which I'm dividing using a Rindler observer into two parts. Are you saying that this number operator will commute with the Minkowski Hamiltonian?
Yeah.
Is that because the state should
the
be
exact Rindler mode? Sorry,
Sorry, the state should be a highly excited state compared to the Minkowski vacuum, isn't it? Because you're breaking the entanglement structure of the vacuum.
Yes. It will, So because the Minkowski Hamiltonian is like the global time translation, and but the number operator commute with the boost operator.
Yeah, exactly. So when you said it commutes, you meant with the boost operator, not
Yeah,
the
the boost
not
up.
the minimum.
Yeah, but it's a boundary Hamiltonian.
So it's the
So
boundary.
the other thing is like we have this ADM mass, the ADM Hamiltonian, and this number operator commute with the ADM Hamiltonian,
Okay.
and you act on it. So from the boundary point of view, it's still in the same energy window, but it
Okay.
creates a firewall.
Got it. Thank you.
Sure, no problem. Thanks for the question. Yeah, please jump in at any time. Okay, so of course this is not like the end of the story, and there in the literature there are lots of different arguments for it or against it. Like for example, this state dependence of this operator, saying like you cannot just keep using this u of theta because it will become state dependent one day you run out of the closed subspace. So it's not sure that all the state will become firewall. And then there's also this frozen vacuums against this state dependence, and there's variation Born's rule, etc. There's a whole history debate about whether typical state have firewall or not. I think it's fair to say like still like the majority of the community is still confused about this, whether a typical state black hole contains a firewall or not. So our work is trying to address this problem, and we trying to do a direct bulk analysis of this problem, trying to see whether there's bulk mechanism that can answer whether typical state black hole have a firewall or not. So let's since we're trying to do a bulk analysis, we were trying to formulate a problem like a little bit bulk friendly. And we can formulate this problem by asking what's the experience of jumping into a late time black hole. Let's consider a generic black hole. Let's say start with thermofield double black hole with some perturbations. Either can be on the left or right, but for simplicity, let's draw the diagram where we have like left perturbations, which is this W. And we consider we jump in as observer from the right side into the black hole. So when the perturbation on the left is present, it creates some dust in the interior. And if we wait longer, a little bit longer time, because the horizon is the interior of the black hole is expanding, everything inside of horizon falling to the singularity. Then, if we jump in at a later time, we do not see the dust, and it didn't hit anything until we reach the singularity. That is showing this left panel's diagram, where the black dot is a observer, the infollower that jumps in. So it just crosses the horizon and hits the singularity. It doesn't see this red particle that the early perturbation is present. And the experience of the infalling observer experience like a smooth journey passing the horizon toward the singularity. And therefore, we call this state is a smooth horizon state. It's like a ordinary black hole state. But we can also consider the infalling observer that jumping at early time here when t is smaller than 0. Then at early time, the infollower will hit this with this W particle, and if the time is like early enough, such that it's scrambling time early than the with respect to the W particle, the collision will be Planckian, and effectively the observer see the W particle at the horizon. Since this proper time crossing the horizon and hit this W particle vanishes. And this effectively becomes a firewall state. The observer immediately dies at the horizon. And we call this a firewall state, or it's a white hole stage, because if we look at this black hole, the interior, as time evolves, is shrinking instead of expanding. So it's a typical feature of the white hole. So this is
So,
Yeah.
sorry, Zhenbin, please excuse me for interrupting so much, but
Yeah, sure, yeah, please.
okay, I understand if the black particle falls in early enough, you get this collision. Why does it look like a firewall from the outside? Isn't it smooth on the outside, just the collisions?
Yeah, it's a smooth outside of the horizon, and it looks like firewall when the firewall problem is whether you hit something jammer at the horizon. So if you jumping from early time, so the enfolder will have very huge velocity at when crossing the horizon. So the time when crossing the horizon and hit this particle and hit the singularity, it's shrinking. So that goes to 0 after scrambling time.
Right, but all the way, I mean, all the way up to the horizon, it's just, you have something falling into the black hole, right?
Yeah, all the way outside the horizon, everything is smooth. That's no problem. Yeah, that is no problem, and that is because the black hole is like it's the perturbation from the left doesn't change the state of the right black hole. So everything outside it should just look like a thermal state. But then, but the problem we'll ask is whether the enfolder have finite lifetime to live inside of the black hole after crossing the black hole horizon.
Yes.
And that for this white hole stage goes to 0 because of scrambling effect, and at the late time stage, in the smooth stage, it still have some finite time to live. Sure. That's a problem we want to ask. Right. Okay. But so this is what classical GR predicts from the panels diagram. But this, unfortunately, this figure is
sorry. Please excuse me, just so I understand the setup properly.
Yeah, it's the most. It's
the issue of whether we have a firewall or not has to do with the behavior at the horizon, right? If I understand.
Yeah.
And so, were you when you called the right-hand situation firewall? Did you have in mind something about the horizon? That's what I'm missing.
So on this figure, it looks like this observer and this like this particle is like kind of some distance from the horizon, right? Oh, maybe that's confusing. But you can try to do like draw a figure that looks like this is at the horizon. So if you can do a like boost between this figure, so make this observer always jumping at time t equals to 0, and this W particle will get boost at the early time. So that will be like effective at the horizon.
Okay, got you now. Thank you.
Yeah, no problem. On the other hand, let's say just for this t, if we do the boost, this enfolder will be here, and this particle will be very late. So everything here is like smooth. So here.
Thank you so much.
Yeah, thank you for the question. Yeah, that's the most important part to formulate the question.
So his understanding is that since it's invariant, since the process is invariant under Lorentz transformations, it should be invariant under boosts also. Is that the argument?
Yeah, there's two. Yeah, there's two. For this geometry, it's invariant under boost. So I can just do a relative boost. So this enfolder jumps in here. This W particle will be here, and here. So what's important is the relative. It's like the relative time evolution between this W and this enfolder. Right. Did I answer the question?
Yes.
Okay. Okay, so this is what the classical GR predicts. But unfortunately, this answer is inconsistent with quantum mechanics. The reason why it's inconsistent with quantum mechanics is the following. So if we combine with quantum mechanics, we know that the Bekenstein-Hawking entropy tells you that the black hole, if it has finite area and finite energy, should have finite degree of freedom because it has finite entropy. And so as we do the different time evolutions, we create a different states, right? So as we jump in different time, we effectively evolve the state by the Hamiltonian of the system. So each thermal time we create a new state. And then if the states we jump in later enough, the state will run over the Hilbert space and become typical state. Same for the early time state. As we evolve the Hamiltonian, as we evolve the state with Hamiltonian early and early enough, it also run over the Hilbert space. And since the Hilbert space have finite dimension, it also becomes typical. So both the late time state and early time state become typical states, but the classical GR still gives you two different prescriptions of the inferrer for those typical states. And that's a puzzle. As a typical state should have like a unique bulk description, although the classical general relativity give you two distinguished bulk descriptions. One contains a firewall and one doesn't contain a firewall. So this is a concrete puzzle that combining GR with the quantum mechanics. Like, for example, for the extreme case, we can imagine T is such late that it runs to the Poincare recurrence time. And then at the quantum state from the boundary, the state should return back to itself slightly early. But the classical GR picture doesn't, of course, doesn't give you the Poincare recurrence. And that is the extreme case of this puzzle.
Sorry, the time scale involved here is exponential.
Right. So yeah, that's here this time scale is when T is order e to the s, e to the entropy, and the Poincare is e to the s. For referring to Poincare recurrence, it's just talking about the extreme case, where the quantum state itself exactly comes back. So
the discrepancy between GR and quantum mechanics is already at
that time order e to the s,
okay,
where you just run out of orthogonal states and become typical.
got it. Thank you.
That's
Sorry, Zhenbin, can I just ask you one more question? I mean,
Yeah.
this state to begin with, before we throw in the two particles, is this thermofield double state of the two boundaries, right?
Yeah.
And
Yeah.
isn't the question of whether we get a firewall or not a question of what happens to the entanglement between the two boundaries?
Right.
Yeah. Okay.
Yeah. Yeah.
Now, is it possible, even though each individual density matrix of the left or right follows what you were saying, our expectation that it should thermalize given enough time, is it possible that the entanglement structure between them has a more delicate kind of evolution, and that is why you're getting in one case a firewall and not the other? I'm sorry if I'm saying something you'll anyway come to, but just to ask.
Sorry, the question is whether
I mean, your next
I think
slide, what it said sounded very reasonable, that if you have a system with some number of states, then if you wait long enough, typically it would thermalize, or become a typical.
It's not about thermalization. Yeah, it's after thermalization. Yeah.
Okay. Okay, let's say it would become a typical state. Sorry, I should have said.
Yeah, right. Yeah.
But here
it's a much longer time scale than thermalization. Yeah. Yeah.
Okay, I see. Okay, let's say, all right, it would become a typical state, but that would be true for each individual density matrix of the left or right. And here we are interested in an entanglement question between the left and right.
No, I thought, sorry, here typical, I mean, so for example, the typical between the left and right state as a like whole state in this time approach become typical. Maybe it's like better to think about so let's think about this W is just a projection operator. Maybe that problem can that way you can think about maybe it's a little bit clear. So the picture doesn't change if W just projected into a simple basis. So we just after projection we got some special state on the right, just a one-side black hole state. And when we evolve, that it's a pure state, and at the early time we still have this different pictures, and when we evolve, the state become a typical state. Maybe that is.
I see. You project the left hand, just so I understand. Sorry, you project the left hand side. You're saying, and in a way, so that then the right hand side is is a, did you say thermal? So that
It's
there
a
are
pure state. I do a full projection on the left. So after that, I got a pure state. And still so that will just be like we're erasing whatever behind this red dot. But whether collision or not, this picture doesn't change.
I see.
And we evolve the right black hole and talk about as typical.
I see.
And the state becomes
You should go on. You should go on, please. Okay, please go on. Please go on.
okay.
Sorry, one question, please.
Yeah.
If you could go back to your diagram.
Yeah.
No matter how late the black dot is, there's always a time early enough for you so that it would disrupt the black dot as well, right?
Sorry, what do you mean?
Yeah. So let's take this black dot where you've drawn it on the left picture.
Left picture. Okay.
Okay. Now I take your red dot on the left picture and put it further to the past.
Further to the past. Yeah.
So I will always be able to find the time so that it will, so the trajectory that starts from the black dot passes the red line now.
Right.
So I'm not seeing the distinction very clearly then. I mean, so why isn't that sufficient to say that at every time you might see some disruption?
Well, right. So you're talking about if this black dot at early, we can evolve the W and insert it this early time, right?
Yes.
In the past, right? But that state would not be a typical state because whenever you insert a particle, that increases the energy of the black hole a little bit, and you need to evolve the state long enough until it again becomes typical.
I see. Okay. So I was thinking of this W as a unitary operator performed on the left.
Okay. Yeah, you can think about that. Yeah.
And you say that if I perform a unitary at very early times on the left, that is somehow is a very special thing to do.
Well, it's not about very early time. It's about, so we're talking about, so this late time. So yeah. So the problem is the following. We're given a black hole state.
Yes.
Okay. So we're jumping at particular time, that state. So here is t bigger than 0. We're giving this state. And we ask what's the experience of the black hole if we're jumping at that state.
Yes.
That's the problem.
Yes.
Okay. So the state is specified by what the operation we acted on the left and what is the history we acted on the right.
Yes.
So that's fully specified. And the question is, given that history of the specification in here in particular, is this with the W insertion and at this time, do we hit a firewall or not?
Okay.
Right. So here we create, with these W insertions, we create a different type of state by jumping at different times, and we got a different, for example, the t bigger than 0, we got a smooth state, and t smaller than 0, we got firewall state.
Yes.
Those are the whole family of states we consider. And between those states, there's some tension between the frequency.
Thank you.
Right.
Thank you. I understand.
Yeah. So if, for example, if you create another W particle here, and then we were going to look a different set of states where we evolve this time even later until we didn't see these perturbations, and those states and have different description with the early time states. But quantum mechanics, those states become similar, so it cannot be the same box state.
Excellent. So your paradox is state by state. It's not really about typicality. It's start with a given state. How can this be?
Yeah, but the paradox comes when the states become typical. When if we become late enough and early enough, both are typical in this in your energy band, and this give you different prediction at what happened at the horizon.
Okay,
and that's
sort of understand. Thank you.
Okay, yeah.
And the understanding is that the two states are related by Lorentz transformations. I mean,
by the boundary Hamiltonian evolution.
Yeah.
But the typicality that is expected is forward in time and backward in time, right? So why is this not a priori okay? I mean, it's not like I mean, sometimes you could have an evolution which would look different. Even both sides are typical, but would look different in the future and in the past, like a gas.
No,
spread in
the
the room.
Hamiltonian is chaotic. So the Hamiltonian is chaotic. So if you apply this Hamiltonian e to the IHT, t large enough, t typically all the e to the s, so this Hamiltonian just become a hard random Hamiltonian evolution, whether t is bigger than 0 or less than 0. So that just maps some special state to a typical state. So the thermofield double with the perturbation is very special state.
Okay.
Right? But after acting on the Hamiltonian, that just becomes this, makes this state less and less special.
Okay. Thank you.
Mhm.
Also, is W related to the e to the I theta NB unitary operator that you showed before?
Yeah, you can think about it, it's that operator, but it's really a very generic operator. This like this shockwave scattering is very general.
And also, I mean, that unitary operator just rotates the B operator by some. I mean, it just adds a phase to the B operator, if I'm not wrong, e to the I theta B. It becomes,
But yeah, that's this AMP's argument. Yes.
yeah. So why does that give rise to a firewall? I'm not very conversant with these things. Why
Right, so-
does rotating the
Because because if that means there's if you're calculating the expecting value of stress tensor at the horizon, it will diverging. If you act in this state, you can do that check. Yeah,
what will diverge?
the stress tensor at the horizon. But here, this W is just a simple perturbation. Let's say you just insert one, like, I don't know, one electron to the interior of the black hole, and then because when you move in early time, there's like a relative boost between these two particles, and that the central mass collision becomes scales exponentially in time, and when the time becomes scrambling, it becomes Planckian.
It's more like a creation operator acting on the vacuum sort of thing.
Yeah. Here this problem. Yeah.
Okay.
Mm-hmm. Right. Okay. So I hope this puzzle is clear to everyone now. So there's this two different box description, but quantum mechanically, those states should look similar. And how that possible? Seems some people say like maybe ADS-FT is not like a map state to state, and so. But I think this is a concrete, just a quantum gravity question, and we should have an answer in the quantum gravity, in a theory of quantum gravity. And there's a conjecture by Susskind saying that in order to this for this two description to be consistent, maybe a typical state have 50% of chance to have having a firewall. And he referring to this scenario as a gray hole for the black hole. The argument is based on complexity growth. He is saying, basically, the argument is the following. So if the black hole, the volume is expanding. So he interprets as the complexity of the state is growing. And in the white hole region, the volume is contracting. And by the complexity equal to volume conjecture, means the complexity is decreasing. But for a typical state, so complexity saturates, so it's like it's constant, so it's never growing or decaying. So maybe it's like 50% of having a firewall component and the black hole component. But this is purely a conjecture, and there was no evidence for this scenario. So in order to, if this conjecture is true, in order to resolve this puzzle, we want some surprises, right? From difference from the GR prediction. The surprise could be if we jump in those firewall states, something could happen, and the enfolder actually experience a smooth horizon. And what the firewall is like already the particle already fall into the W particle already fall into the singularity. Or if we thought we jumping into the smooth horizon states, but then some miracle happens such that we hit the firewall at the double particle immediately at the horizon. And where I think, so one nature question is, are there gravitational processes that bring you this surprise? And does that give you a firewall for the late-time black hole? So this is our work. So in our work, we propose a specific bulk mechanism that supports the Susskind conjecture. And this bulk mechanism is based on the chaotic nature of the black hole. We argue that by emitting a very large baby universe, a black hole can tunnel into a white hole and therefore contains a firewall if it's not a thermofield double state. So with a generic perturbation. And furthermore, we calculate the probability of hitting a firewall given there's one baby universe emission. The probability is given by 1/2 times t squared times e to the minus 2s, entropy of the black hole. So let me explain the factors. So this e to the minus 2se is typical for the baby universe emission process because a topology change process. And whenever topology change, you have some gravitational action. It's an instanton, and that have the action given by proportion to the area, therefore the entropy of the black hole. What's surprising is that this probability scale is time squared. So when t is order e to the s, these two become same order, and the probability become order 1. And that is suggesting that for a typical black hole, there's a order 1 probability of hitting a firewall. And furthermore, there's a 1/2. This 1/2 actually suggests maybe the probability is 50-50, but that is a pure speculation. So this talk, I'm mainly focusing on explaining these two statements: why emitting a large baby universe give you a firewall, and how do we get this probability?
So what is
So
the
that's
measure from?
Sorry?
T is measured from what point?
From where the W insertion is present. So where the relative booster is 0.
Okay, thank you.
And Zhenbin, one question. If I take t to be e to the minus s in this case, or sorry, no, I suppose
Minus e to the s.
Yeah, I was wondering what happens. Yeah, but okay, I see. It's
Yeah,
invariant
it's,
under t.
absolutely, yeah.
Okay, thank you.
So let's first, so I think the mechanism is based on quantum chaos. So let's just have a one slide review for quantum chaos. So black hole is a quantum is a very chaotic quantum system. So the one of the very well studied quantity in quantum chaos is a spectrum form factor, where at late time it have a universal behavior by random matrix theory. So the spectrum form factor is given by the analytic continuation of the Pachin function, z times it, where it's trace e to the iht, the modular s squared, which you can also interpret as the inner product of the thermofield double evolve at time t with thermofield double at t equal to 0, so norm squared. And the random matrix theory tells you that in the GOE case, so without any time reversal symmetry or whatever, the late-time spectrum form factor have a linear ramp piece, t times e to the minus 2s, and then it saturates to the plateau, e to the minus s. So this non-zero value of the spectrum form factor tells you that quantum chaos protect that the thermofield double at the late time always have small probability of returning to its initial state, here given by t times e to the minus s. So t order e to the s, this is exponential small. It's e to the minus s small. This little tiny probability of return to its initial state. In gravity, this linear ramp piece of the spectrum form factor is explained by Stanford, where they explain that this spectrum form factor comes from cylinder geometry, where each boundary is a boundary of the patching function. And then there's a baby universe exchange between these two copies of the system, where the baby universe have size B that scales linear in T. There's 1/square root of energy, make it dimensionless. Well, not dimensionless, but just make it the correct scaling. And then this linear in T factor coming from the relative twist around this closed geodesic. So that's a story of the spectrum form factor. So if we cut around this cylinder, so here at each boundary, it's another continuous spectrum patching function. So it has some Lorentzian time evolution e to the IHT. We can cut it separated by time evolution of T and A minus T. Let's call this size of baby universe as A. Then we can interpret this geometry as calculating the norm squared of the thermal field double state with time T with the thermal field double state with time T minus A. So here is a boundary preparation of the thermal field double state with time T, and here it's a thermal field double state with time T minus A. And because it's complex conjugate, we add the time evolution by A minus T, so that the total evolution is order A. So this geometry we can interpret as saying what? As saying the spectrum form factor also describe thermal field double state can return to an early time state. In other words, an HT black hole state, this thermal field double state, can tunnel into a HT minus A black hole by emitting a baby universe of size A. So that's what this inner product means.
Sorry,
Right?
Zhenbin, I didn't quite understand why the place where you cut the boundary, the T minus A, the A there, why is that related to the modulus, the size of the wormhole?
Right, that's because on this, on this spectrum form factor, this boundary evolution is T, and this closed universe is order T as well.
I see.
And that's the geometry. That's like the.
I see.
That's a geometry, and here on this geometry we cut it. So this boundary and this alien has the same time.
Perfect. Thank you.
Yeah. Okay, so a cartoon picture of this statement is the following. So we consider a late time black hole, right? And if we look at the nice size of the black hole, then it will becomes approximately a cylinder. It will have some constant transverse area because the nice size will tend to have the same transverse area, and then the radial direction, the volume grows linear in time. That's this linear. That's what this horizontal line represented. It represents the volume of a late time black hole. It grows with T. The effect of emitting a baby universe can think about it as a pinching process where we pick up 2 points and make it close. That's always how we visualize baby universe emission. The volume is approximately conserved during this process. So if we emit a baby universe A, then we're left with a new interior where the volume is order T minus A. And that means the age of the black hole is T minus A after baby universe emission.
Question.
Yeah.
Shouldn't you also be considering whether energy is also conserved or not?
Yeah, in this process, the energy is conserved. Yeah.
And
So
The energy
much,
of the boundary Hamiltonian, yeah.
how much energy is carried away by the baby universe? Presumably
Or it
zero.
should be 0, yeah.
So is this process totally delocalized over time if it carries away zero energy? How can a process with zero energy be localized anywhere in time?
Well, it's not localized, so you have to integrate out. So that you have to analyze it.
So
right.
This is some integrated probability over all time.
Yeah. They have some so generically, because you have some Lorentz evolution where you emit the baby universe, you have some phase oscillatories. But those, if you calculate it properly into account, that will give you the probability that I described. But I'll describe those. Yeah.
I see. No, I'm sure you'll come to this, but your final probability had a time t square e to the minus 2s, right?
Yes.
And that was the probability to emit a white hole with zero energy, right? Or am I confusing?
The energy of cross universe obviously is zero because of the Hamiltonian constraint, right?
Sorry, please go ahead. Maybe I'm
the energy of a closed universe is always zero because of Hamiltonian.
I would have thought so.
Yeah.
So okay, maybe we come back to this. But so I mean, how are we associating a probability per unit time or a time t with a zero energy process? I'm not entirely clear how that happens.
Sorry.
It's different
Sorry.
from alpha decay or something, right? The decay of some particle which carries away energy.
So this is generically sound like Euclidean process. I don't know how to think about it as some particle decay. Yeah, I don't.
Could it be imagined as a soft particle emission?
Soft particle emission.
In a what happens
maybe
in a soft emission, in a soft
maybe soft but period. Yeah, just to see why this energy is conserved. For example, this spectrum form factor, this is really considered about when the energy, it's a fixed energy ensemble. So this state early and late have the same energy. So after, like, it's a state with fixed energy evolve at time t, come back to this early time state with the same energy. Same here. Yeah. So like this energy is this boundary is just fixed. This baby universe doesn't carry any energies, and you integrate over where this can happen. So it can happen like here, like anywhere around this slice, or it can be happen like early time. You have to integrate it over. It's given by some like some wave function of the JT gravity.
Does the wormhole in general have a tension?
Sorry?
Does the wormhole in general have a tension on its surface?
Wormhole have a tension
on its surface.
On its surface. I never thought about that problem. I didn't encounter any tension on this one.
But if it has a tension, then I mean, a certain section would also have a mass, I think. No?
I think it doesn't have any tension because this moduli of this baby universe is like it's like some zero mode integral. Right.
Yeah. So you're saying that because of the Hamiltonian constraint, the energy is zero. That's what you're saying.
Yeah.
But I mean, isn't that in contradiction with the fact that if the wormhole has a tension, then
no, I think the wormhole does not have a tension. Yeah.
Zhenbin, one question. So the fact that you integrate over T, is that the thing that gives you this extensive factor?
Well, we will go to the extensive factor. It's coming from integrating over the baby universe. Yeah.
Okay.
Yeah, because when A is bigger than T, so let me finish this. If A is bigger than T, then this apparent H becomes negative, and therefore the new state becomes a white hole state, or therefore a firewall state, and the probability will coming from integrating over the size of the baby universe, right?
Okay.
Yeah. Yeah, the spectrum form factor is exponentially small because the size is fixed. So we only have this relative twist. So that gives you a single factor of T. But then if you're integrating over the size of a baby universe, the probability that the black hole can emit a very large baby universe, then give you additional T factor, and that makes this order 1 probability. That's the idea. Yeah. Okay. Right. Yeah, just draw another cartoon. So if we jump in a late time, but emit a baby universe, this A, then if effectively it brings a state at some negative time evolution of time order proportional to A. So you jump, if A is bigger than T, you jump in, you hit a firewall. So that's a first picture, right? Of course, you can calculate this, the wave function of, in JT gravity, you can calculate the wave function of emitting a baby universe, and you find this, what I said is correct. Yeah, you can literally derive it.
Yeah, sorry, Zhenbin, just I'm having a little trouble just understanding the double trumpet, although I should be able to. But you're interpreting the small circle at the center as the baby universe, if I understand, huh?
Yeah.
Right. And just if I want to match this Euclidean instanton to the final Lorentzian state, how do I cut it? So that at some instant I then match to a Lorentzian configuration involving two boundaries and the baby universe, please. Yeah.
Right. So you cut it. Let's say you first cut it out here, and then you cut it here. So you got a slice of this. Let's call it L slice and the baby universe. And then here you have the same copies, but then the baby universe exchange between these two systems.
I see. So is it that you have the two boundaries, and you have in Lorentzian space, you might say that you have two boundaries to begin with, and in the far future, but when you actually think of the Euclidean process, there's a baby universe being exchanged between them. Is it like that, or is it that finally in Lorentzian space you have the two boundaries you started with and a closed baby universe? What is the picture, if I may?
Right. So if you right. So I think that's right. So so in this particular feature, in this particular graph, at this time, if you have two boundaries, so if you cut it, you got at least two slices, which are these two blue slices. Yes. But then you additionally can cut it over A, and that gives you this baby universe. So it's two interior of size T minus A and a baby universe of size A.
Zhenbin, is it like if you have an exchange diagram with some, let's say, a mass, light particle getting exchanged, from there you can also compute the decay rate, which is just cubic vertex. So is it like that? That this diagram is like the exchange diagram, but you are just focusing, let's say, on the left side and then looking at the emission process.
Right. It's like, it's like that.
Okay.
Right. But this is really just okay. There's some caveat, like this problem, this double trumpet geometry. It's just a heuristic argument. It's actually, it does not, what we're really thinking about for the later, it's not this double trumpet, it's really actually a handle cylinder. So it's just purely a one boundary process. So this is just to give you a quick derivation of this large baby universe emission effect. Right.
And then one quick question. If you evolve to the past, like if you had jumped at a very early time,
right,
is there a similar process which will give you the half probability of encountering a smooth geometry?
Yes.
Okay.
It can add or subtract.
I see. Yeah. Okay. Thank you.
Right. Okay. Right. I think I should add a slide to show you explicit formulas how this process works, but unfortunately I didn't prepare that. But you guys can look at in our paper the explicit wave function calculation to verify this. But here I just ask you guys to trust me this picture. Okay. So the second problem is to calculate this probability of hitting a firewall. So before we just said
Sorry, can I ask a question? So is the opposite? So you said after the baby universe is emitted, the age of the black hole becomes smaller, right?
Yes, yes.
Does the opposite process also happen where it becomes larger?
Right. So if you, yeah, so it's also, so
So
if
if
you're
you
jumping early time, you're emitting baby universe, it can make it larger, right?
I see. So then the size of the baby universe that's pinching off is larger than I'm slightly confused. It's larger than the size of the
The absolute, yeah, then it becomes smooth, right?
okay.
Right.
And sorry,
That's
Zhenbin,
right.
just to make sure I completely understand, at least
Mhm.
if I were to state everything in Lorentzian terms, we start with two boundaries which are entangled, and we end up with two boundaries and an extra closed universe. Is that
Yes,
correct?
yes, yes, that's right. Yes, that's right.
Okay. Thank you.
Mhm. Right. Let's look at this picture. Maybe it's a bit clear. So just, so here we are actually looking at the one single part copy of system. So we have this thermofield double state, and with time evolved, and then there's a Lorentzian, so Euclidean, there's a Lorentzian evolution between these two sides. Let's forget about the labels. So that's a state, boundary state. And then in the bulk, you have some Euclidean process of emitting a baby universe of size A. And that give you, if that give you a new slice, this L is a interior slice after emitting a baby universe A, because L is a size that yeah, that is like, I don't know what's the mathematical term. It's like non-intersecting with A. And so this is a process of, so this is a new spatial size after baby universe emission. You get a size of L and a size of A. That's when you cut. And if you glue this together, you got this handle disk geometry. Is this picture understandable? Okay. Well, yes. So there's this is a boundary.
You're essentially emitting and absorbing back the baby universe, right?
Yeah. So this is the bra and the cat. So when you're taking probability, you're taking inner product of the state with itself. So the baby universe, you trace out the baby universe. So you got some state here.
All possible ways of emitting and absorbing the baby universe.
Yeah.
Wait, and for the Lorentzian process, you'll cut this in the middle and then evolve in Lorentzian time. Is that right?
Yeah. Oh, the Lorentzian time is already contained in this when we cut it. This is the end point of the Lorentzian evolution. So the Lorentzian time is already here, although I didn't show it. Here, this is like the beta over 2 plus the IT. This already have the Lorentzian.
Yeah. So suppose this diagram was just completely Euclidean. Say on the left, it was just purely Euclidean time. Then I could take that, cut it in the middle.
Yes.
And then later evolve in Lorentzian time, right? That would give me the final state of this instanton. Is this correct?
Yeah, but that effectively is like, because when you evolve, you're moving this black dot later and later. It's like effectively is like adding Lorentzian time on this boundary.
Sure.
Yeah.
Sure.
Yeah. Yeah, we are saying the same thing.
Yes. Okay. Thank you. Yes.
Zhenbin, from this diagram, is it clear that the evolution process effectively reduces the age?
This picture, it's not very clear, but it's kind of clear if you become a little bit familiar with with these geometries. So what's effectively going on is like the following. So before this emitting of baby universe, you got this L1, this interior, and after emitting baby universe, you got this L and this A, right?
Yeah.
So I think it's true for general higher dimensions, but let's just, for instance, thinking about it in JT gravity. So where here this spatial geometry is a constant negative curvature. Okay, then this area of this thing is finite. Does not is given by the genus, so it does not change when you're increasing A and L1, and that means if the A is bigger, A is big, L is big, and L1 is big, these three sides these three boundaries almost follow each other, and that reduces to some linear additive relation between this L1, L, and A. Basically, L1 is L plus A.
I see.
So in the case of a high dimension black hole, you can think about a late time size. The transverse area is like some sphere have some constant. It's a constant transverse area, so it's like you have some like constant constant positive curvature, and that give you some this two-dimensional geometry effectively has some constant negative curvature, and that gives you the same effect.
Okay, thank you.
No problem.
Also, one question which may be kind of stupid, but if the state at time t is going to state at t minus a, then is it like there is a non-zero probability that you tunnel into the past as a time machine?
No, it's not a time machine. It's like it's adding some negative time evolution. So it's evolving backwards. It's not like a tunneling to the past.
Okay.
Just like in ordinary quantum mechanics system, we start with any time. If we have control of the Hamiltonian, we can evolve it backwards. And it's not keeping track of what type of perturbation you inserted in the past. It does not contain that memory. It's just a straight time evolution.
I thought you were jumping at a particular time t, but you are feeling the effects as if the time was t minus a.
Yes. But you are not able to like jump in and like kill yourself at early time. You do not have those time machines. Yeah.
Okay.
Yeah. That requires this negative time evolution to depend on the state. This negative time evolution is just given by the boundary Hamiltonian. It's not dependent on state.
Okay.
Sorry, just to make totally sure I'm understanding. Is before the baby universe is created, your space was an interval, and then there was time.
Yes.
And after the baby universe is created, your space is an interval times time plus circle times time. Is this right?
Yes.
Okay.
That's right.
Thank you.
Right. Okay. Yeah. All right. So let's try to calculate this probability. So the naive calculation, the probability of hitting a firewall is the following. So we have this topology change process that gives you e to the minus 2s. And then there's this, we're integrating over the size of baby universe. So there's two parameters. There's this baby universe size. In order to become a firewall, we want the size to be bigger than t for time t state. And then around this baby universe, we have some twist parameter. And the S will run from 0 to A. And the result gives you nonsense. It's an infinity. And this naive calculation is wrong, saying that because it does not take in account of large diffeomorphism symmetries. So there's discrete symmetries that constrain this probability integral and make this probability finite. And that's what we are going to talk about later. So we will start this problem in JT gravity, just constraining this large diffeomorphism symmetry. Where it's a two-dimensional dilaton gravity with constant negative curvature. It's ADS2 space. Those high genus wormholes becomes Riemann surface. And the large diffeomorphism symmetry becomes a mapping class group on the Riemann surfaces. And the mapping class group can map the process of emitting a large baby universe to a smaller baby universe, therefore reduce this integral. So let's look at how this mapping class group works. So here we have some, let's say we have this handle disk geometry. We cut this slice L with a baby universe A. But we can, mapping class group will map this size to a different size on this geometry, and then there will be different baby universe A. And we need to somehow fix this gauge constraint. We are interested in the limit, as I mentioned before, we are interested in the limit where the time is large. So the geodesic slices, this L and A are also large, grows with time. It scale with e to the s, very large. But the area of those Riemann surfaces are fixed, cannot grow with time because those are fixed by Gauss-Bonnet theorem. The Gauss-Bonnet theorem tell you the total Ricci curvature of the integral is constant, given by genus, but since it's constant negative curvature, that means the total integral of the area is constant. In this limit, the Riemann surface becomes a strip. So, the two process of emitting baby universe can be visualized as these two different pictures. So this picture, so the same black and red dot, if we are emitting a baby universe with a size smaller than t, in other words, it turns into still a smooth horizon state, the geometry looks like the following. So we have this new interior size L, and then there's old interior size is L1, scale is t, and then this L1 just circle around this baby universe A. And therefore this L, for example, is like have size t minus A. And we have bra and cat. So there's two bra and cat. These two A's will be glued together with a relative twist given by the S parameter, the twist S. And on the other hand, if the baby universe...
Sorry to interrupt.
Yeah.
So do I understand right that if you start with an interval, and then when you emit to the baby universe, your interval becomes smaller, roughly?
Yeah, this is the starting interval.
Yeah.
This outside interval. And after emitting baby universe, I get new interval, right?
And this is the loss of complexity that you were talking about earlier, right?
Yes.
That it keeps, yeah. Thank you. Yeah.
Mm-hmm.
Zhenbin, actually, the previous slide was somehow easier for me, and I was thinking that's what you had in mind, that basically you have a disk with a handle.
Yes.
And then you cut the disk at whatever location along the circle to get your two boundaries at that time.
Yes.
And then your handle also you cut in the middle.
Yeah.
If we are talking about matching the Euclidean to Lorentzian.
Yeah.
Right. And so you have this handle which you have cut, and you have a one-dimensional locus, which is sort of the instantaneous baby universe, right?
Yes.
And then just to understand fully the Lorentzian continuation, of course, the two boundaries you continue into Lorentzian space.
Yes.
And what do you do with this handle that you have cut in between? That also is continued to Lorentzian space? Or?
Well, that will just be we will integrating over the size, right? We need to integrating over all the possible universes, and because there's this relation between this L plus A with the Lorentzian time evolution t, this A will be like when we're changing A, this interior L will changing.
Yeah, but I mean, you have to match it to something in Lorentzian space, right? So you continue it in some way to a disk, to what, a single?
As Shiraz says, it's like interval times a circle. Interval plus a circle. Sorry.
I see. I mean, the only asymptotic solutions in ADS JT would have been negative curvature.
Yeah.
Yeah. Okay. Go ahead. Please go ahead. Yeah. Okay.
Right. Okay. Yeah. So just say again, we start with interval where size order t, and after tunneling, we got an interval with size L plus a closed circle with size A, and the L plus A is equal to LT. LT is T. So that's this picture.
So why is there like a cusp in this first geometry?
Where cusp? You mean here?
Yeah, I mean this. Yeah.
Yeah, it's not cut. It's like smooth. Yeah, it's just a carton. Those will be glued together. Yeah.
Okay.
So for the firewall state, if we emit a baby universe size A bigger than T, the geometry looks the following. So it's a strip, right? So we have a initial size of order T, and we emit a baby universe. So A is bigger than T. So it means this initial size cannot hug around A. But the initial size together with the new interior L, that can enclose the baby universe A. And that gives you the relation that the L becomes A minus T, A minus LT. So that's the effect we're talking about. So so when we, for example, if we evolve the time, we increase T gets larger, then L becomes smaller. So that's saying the time, as time evolves, this new interior is shrinking, and therefore it's a firewall state. On the contrary, here, if we fix the baby universe A and we increasing the boundary relaxing time evolution, as you guys are seeing, then LT is increasing, L is increasing. You got this smooth. It's in other words, the interior is still expanding, and you got this smooth state. So that's a strip picture.
So relationship with the previous disk diagram is obtained only when you glue the two circles together, right?
Yeah,
I mean,
yeah. You glue the two circles, then there's a relative twist. You need to interpret it. So that's where the mapping class group is coming from.
Yeah, yeah. And of course, there's also the fact that that what you said, that A and some modular related value is the same. So you have to mod out by those.
Yeah, yeah, I'm going to talk about it. Yeah, here, this slide. Right, so let's look at how the mapping class group acts. Since we are interested in the firewall, we will just look at those firewall states. So when A is bigger than T, so we got this strip picture, and when we gluing these two baby universes, we need to identify how they are glued together. So there's a twist parameter. So it's S. So S means this point is glued with this point. Okay, so if let's first look at when the twist parameter is smaller than this interior size L. So in other words, it's this configuration. Then the mapping class group maps this original L size to a new L size. For example, this new L size, we can consider just go through this identification. This, if we draw this new size L size horizontally, give us this picture. These two are identical wormholes because I didn't change any modular parameter. I just cut it differently. But those corresponding to different baby universe emission size. In particular, on the left, we have baby universe A with a twist S, and then we have an interior L. The mapping class group maps it to A prime, S prime, L prime, where A prime is A minus S prime is still S, and L prime is L minus S. So it both reduces the size of the baby universe and reduce the length of the interior. But still, it maps, and these two are both firewall states. In other words, the mapping class group can map different baby universe sizes, and that reduces the number of the firewall state. In other words, in the previous calculation, we are overcounting a lot of the geometries because we didn't divide it out to the mapping class group.
Zhenbin, one question. Is it at the end an integral over the moduli of a torus with a hole cut out?
Sorry?
If you have a torus, if you
torus with a hole cut out. Yeah.
Then you are doing an integral over the moduli of this and writing the function as a function of the size of the hole.
that's roughly speaking is right, but then there's a additional thing because we're interested in the firewall component. So you need to conditioning on this complement size, this L size, to have to be a white hole, to have a firewall. So that's a condition, that's a constraint. Otherwise, it will just becomes patching function, genus one patching.
So it's basically integral over some part of the modular space.
Yes.
Some boundary in the modular space, after which it gives you the firewall, and you integrate over that part only.
Yes. That's right.
Thank you.
Right.
Sorry, one more question.
Yeah.
In the case where the baby universe emission did not create a firewall, you reduced you had an interval and its size got reduced. In the case where it does create a firewall, what is the final geometry at the end?
It's still a slice L and the baby universe A.
It's a slice L joining the two boundary points.
Yes.
But then how do I see it's a firewall? Sir?
Yeah. How do you see it as a firewall? Yeah. So as I said, the firewalls, right? Those firewalls, those slices. One feature of this firewalls, it's a white hole state. Means if we evolve this time in the future, this size getting shrinking. This size just getting smaller and smaller. And for the smooth state, this size, the L size is expanding. So it's like the first derivative of this size tells you it's a firewall smooth.
Yeah. Is it the extrinsic curvature of the slice as embedded in the higher dimension, in the 2 dimensions? I mean, if you take 2 slices of the same
the extrinsic curvature tell you the change of the size. Yeah.
That's what I thought you were saying, that you patch, but now your extrinsic curvature has changed sign.
Yes.
See.
So you can. Right. In other words, the derivative with the length is right. So here this length is expanding, and here the length is contracting. Yeah. So here when we increasing this L boundary, increasing this LT, this L keeps like getting larger with LT, with A fixed. Here, on the other hand, if we're increasing LT, this L getting smaller because the LT can hug around the A bigger. So this L getting smaller.
But sorry, just since it's a firewall, shouldn't I have seen something dramatic happening somewhere in the middle?
Well, here it's we're drawing this geodesic size. So in this firewall state, we're drawing this size.
Okay.
What's dramatic happening is when you do a Lorentzian evolution, like when you do a net continuation, there's a dramatic happening.
Fine.
Here.
So you say you have to evolve to see that there's some drama in the middle.
Yeah. You can evolve with a weird width constraint.
Okay.
Right. Just drawing different sizes.
Thank you.
Mm-hmm. Right. Okay. So this is the mapping class group. If the twist is smaller than L. Sorry, is that a question?
Why S is not changing under this transformation?
A? Why S is not changing? Well, it's just in this case it's not changing. You can work it out. Yeah, it's for example, if you you can work it out. It's not that hard to figure out. It's S is not changing.
S was the twist along the handle when you glue it?
Yeah.
Was S the twist? Okay, thank you.
Yeah. Right. So, but this mapping class group reduction will terminate when L is smaller than S. That's because if L is smaller than S, so the two twist is like here. Then if we if we draw this this new interior slice, this mapping class group give you the new geometry becomes when we the new baby universe complement to this new L size will look like this. And this is the offshore geometry. This is when the mapping class group maps an onshore geometry to offshore geometry, onshore size to offshore size. It's offshore because this angle is not perpendicular. So when you're integrating over these geometries, you're integrating over the angles, it's oscillating, and this geometry gives you 0 contribution. This size gives you 0 contribution. In other words, the mapping class group stops at when S is bigger than L. There's actually a nice geometric meaning of this condition S bigger than L. So in previously, when S is smaller than L, it means on this L size, there's two distant locations actually have shortcut. So this point can go through this baby universe and enter in to this point. That means there's no spatial locality on this L size. If I look at measuring correlates, we'll find large correlations, even though they are far apart on this L size. But if S is bigger than L, then there's no points on this L size that have a shortcut. So if we measure the correlations, it will just decay as ordinary spatial size. So it's a very nice geometric meaning. And so we can impose this no shortcut condition that fix this mapping class group. So we get S bigger than L, and similarly, S can be negative. That just flips this diagram left, do a mirror reflection of this diagram. So that also requires A minus S to be bigger than L. And we have L equal to A minus T. So this no shortcut condition gives us this following condition. S has to be bigger than A minus T and smaller than T. So S bigger than A minus T is coming from this first requirement, and S smaller than T is coming from the second requirement. And combining these two, this gives us the size of baby universe had to be smaller than 2T. And since we're also looking at the firewalls, A need to be bigger than T. That gives us a bounded moduli region of this baby universe. So if we're integrating over this fundamental region, then we got a firewall probability is T squared over 2. Basically, this S integral gives us 2T minus A, and we integrate over A with from T to 2T, that gives you T squared over 2. And that's a result I introduced at the beginning. It becomes order 1 when T is order e to the S, which means it has significant fraction of probability to hit a firewall if you're jumping a very old black hole. So please do not try to do that experiment. Okay. So this is a major part of the talk. I think I probably already used too much time. Sorry for that.
Sorry, could I ask a?
Yeah.
It's not a question that perhaps goes beyond your calculation, but suppose in addition to this 2D gravity, you had some matter inside. So you had a rocket ship moving in this thing. In the region that was going to become the baby universe, will the rocket ship escape into the baby universe?
When you insert this rocket ship. Sorry, I cannot hear you, Schwartz.
Sorry, the rocket ship was inside. It was some matter field inside around the time the baby universe was formed.
Around the time where baby universe is formed?
Yes.
Right.
Because Lorentzian geometry, it's a geometry with space-time. This interval has a rocket in it. And then the baby universe is formed. Can the rocket ship be carried away into the baby universe?
Yeah, in principle it can, yeah. But whether that to give you a large contribution, I think it will not, because the rocket ship will become forming a it will have some like forming a circle when you grew this brown cat, right?
Yes.
And then because in this most region of this most region of this integral, there's no small circles.
Okay.
Other circles are large, so that means the locker shape will, whatever the matter loops, those will be suppressed, because those are some Euclidean geometries.
Okay.
So the Euclidean circles, it will give you like e to the minus ml, and the size is like grows with t, so it's just becomes very small, negligible.
So does this mean that if I fill my space with stuff, there's a gas inside, then this suppresses the probability of forming baby universes?
No, feel the fills the space with sizes.
With stuff, right? There's a matter field, there's a gas of matter inside, and now you do your calculation. Does that mean that this suppresses the baby universe formation process, or does it mean that some of the matter will go in, or neither?
Let me think. So if you
see, we've got JT gravity with some conformal matter in it, and it's in a state where the matter is in some gas state.
Right. So first of all, if it's if JT with matter, if the matter is in a thermofield double state, in a Hawking state, the effect does not change, right?
Okay.
So you are talking about if the matter is in some other state, it's like in some thermal state, whatever state, right? You ask whether the effect will change. I think that's a good question. It may change. Yeah.
Okay. Thank you.
Wait, yeah. We didn't analyze that problem. Yeah.
Actually, sorry, this is probably all an aside for you, but just to say, even if the matter is in Huttle-Hawking state, the one loop effects are dramatic because, as you know, there's the analog of the tachyon divergence. So
right. Yeah. So there's an analog of tachyon divergence. So I was imagining there's some like UV completeness to fix this tachyon divergence.
Okay.
So right. So those tachyon diverging, those matter loops can be important when this S is small. So that when the S is large, those are not important, because this will not be no short circles. But if S is small, those potentially become important. We didn't analyze those problems. My feeling is those will not be important, because those does not have large moduli integral region. But I don't want to commit to that.
Yeah.
To that statement.
Yeah. Usually, just to say, if you just compute handles in JT gravity, say handles on the double trumpet or on the disk, it's a very small corner of moduli space, but it's a very strong divergence.
Right.
So it just dominates
right.
them. Yeah. So you'll need some cutoff, but okay, never mind.
Yeah. So you probably need some cutoff, and then whether that cutoff, I guess the cutoff should be time independent. So at later time you can make it small. That's my feeling. But
yeah. And Zhenbin, let me also just in continuation just ask what's really behind the question, which is that if there's some matter inside and it disappears into the baby universe, then it naively feels that the boundary theory no longer knows about that matter. And I was wondering how that was consistent. You know what the picture was then.
Yeah. Sorry, if there's a matter that fall into the baby universe.
That's right. That disappear. It seems like its tails no longer reach the boundary now. So what's the deal with that?
Yeah.
Right. Matter falling into the baby universe and it never reach the boundary. Right. So in that case, you won't say that matter field.
That sounds like conflict with unitarity on the boundary.
Yeah, exactly. That's right. Sorry, but I was no. Thank you, Shiraz. I also had this. Is the two boundary state after emitting the baby universe in a pure state? To begin with, you're a thermofield double, so it was pure. Now you emit the baby universe. Have you not lost some information in general? I think Shiraz, just to put it like that. Yeah, but okay.
Right. So I think that's a very good question. So. Right. So that's the following. So I think we're looking at the infalling experience, right? So for the infaller, will see a mixed state because the infaller didn't see the whole geometry. So I don't think there's any loss of unitarity for the infaller. So you may ask what happens for the global size. If I just cut it to the slice in the middle on this L slice, it seems to be in a thermal state, in a mixed state, because we chase out the baby universe. But that's a little bit too quick, because in order to check whether that slice is pure or not, you need to use the island formula. So the island formula will tell you that there's a quantum extreme surface that is circle around this closed universe. So this closed universe is actually in your entanglement wedge of this L size.
I see. Just say again the island. Could you just repeat that statement once? Sorry.
Right. So I think the puzzle is if there's some matter inside of the baby universe, and then this looks like this slice lost the information of this matter. But that's just like if you have black hole that fully evaporates, there's some matter inside of the black hole itself create a baby universe. But it doesn't mean the information is lost. On the other hand, you should just look at the quantum extreme surface on this slice, and that will include the island on this baby universe. So the whole thing is inside the entanglement wedge.
So are you imagining there are these quantum ER is equal to EPR wormhole between the S1 and the interval that conveys the information somehow?
Yeah, the island is a more mathematical refined version of that intuition. Okay. It's just a very mathematically like the quantum extreme surface, the replicable wormhole will just include this closed universe. Yeah.
Okay, thank you.
Sorry, Zhenbin, one question, perhaps naive. But you said the baby universe will not carry any energy, right? So how can the matter go inside it?
Well, then the matter will project to the zero energy state. Yeah, it has to be projected.
What?
Yeah, the matter has to project to zero energy state or zero momentum. Yeah.
To what? To what? Which energy state?
Zero energy state.
Zero energy state.
Yeah.
But why would it have a zero energy state? I mean, matter will have energy, right? I don't know.
Well, in other words, the component where the matter have zero energy will go into the baby universe. It's a general feature that those closed universes cannot have any gate charge. For example, you can just think about if there's an electron. Can one electron go into the baby universe? The answer is no, because if there's an electron here, the electron will have some create some electric field, but the electric field has to go back. So that's just not satisfied with the Gauss's law. So it has to be like electron and the positron pair together going to the baby universe.
They can have energy, right? The electron-positron pair can have energy.
Yeah, well, you need to, but then you also need to, because you have to impose in Hamiltonian and momentum constraint, those also have to project to the zero energy state. Sorry,
then that overlap is just zero, right? Why is there a non-zero overlap between zero energy state and electron-positron state?
Right. So I think that perhaps means it's right. Naively it's zero, but actually it's not literally zero because it has to, yeah. This you need to go to the I need to right. This is because when you insert this it's just some, perhaps it's some theory with the ensemble average. Maybe it's some, maybe it's a feature of ensemble average. Let me just say the following true statement. So if you insert in, for example, in JT gravity, if you just insert a particle, and then it's a one-point function. So naively you think about a one-point function should have expecting value 0, because it cannot have zero, its zero energy component is 0. But actually this one-point function is not 0. Field size show that due to the wormhole effect, This 1-point function can be non-zero. That says whenever you insert a particle in this in the JT gravity or in this ensemble average gravity, there's always a small component where this particle have zero energy.
Okay, I have to understand that, sir.
Yeah.
Zhenbin, maybe this is related somewhat, but just there's something that's really bothering me, which is, coming to this closed universe, as you know very well, JT ADS gravity has no classical solutions which are closed universes. Because ADS means, you have boundaries. If you are working, at the sphere, at the zero genus, or you have these handle things. So what is your baby universe going to evolve into? Does it recollapse?
I think it's a collapse. It's a collapsing universe. I think it's right. So this is for example, for the trumpet. You can think about it's a process of the baby universe is like the geodesic on this trumpet. And that, if you do an continuation of the metric, you find it's collapsing because the Lorentzian constant negative curvature closed universe, and that is just collapsed.
Okay, so you say you produce it at some instant, let's say when you cut your Euclidean diagram, but then it just recollapses back.
Yeah, it's a crunching.
If it's going to work.
This universe is analyzed by Chen, Madasina, and Gobanko in this bracket wormhole geometry. Basically, this is like the bracket wormhole. The bracket wormhole is like you're gluing these two boundaries. So there's this universe and this universe. And this universe, when you do an continuation, you find it crunch.
Okay.
Is this the analog of the ADS for geometries we study in cosmology with S3 slicing?
Yeah, it should be the same. Yeah.
So, Zhenbin, one question. When you were talking about this rocket ship, you said that there are large circles, and from those circles, you will get a factor of e to the power minus ml.
Yeah.
That's as if you're talking about some energy m in the baby universe, right? So you're not quite even projecting on the zero energy state. So getting confused about this whole thing.
Right. So that is if you fix the twist, right? But then you need to integrate over those twists, and that I think effectively will project it to the ground energy state.
It will give you e to the minus ml, where m is the mass of this rocket ship.
Right. Yeah. So I think you need to distinguish with the energy measured by the ADM mass versus the local energy you're measuring, right?
But then, when the rocket ship had gone there, you would have less mass in the original universe, right?
I'm not sure. I don't. Yeah. Let's see.
I mean,
no.
Sorry, you be about in terms of correlators, which go from one point to another, and when you have the wormhole, it threads the wormhole in some way, and it acquires a certain extra piece. Is that what you're saying?
Sorry, I cannot hear you. Can you say?
Instead of talking about rocket ships, shouldn't you be talking about correlators, which join two points on the disk?
Right. So let's look at this example. So maybe that can be clear. So we insert a correlator, and this correlator there's a geometry, that wormhole geometry give you this one. This is studied by Phil Sapp. Okay, there's this baby universe. Right. Okay, so this baby universe has some size b. So can you see what I'm drawing here?
Yeah.
Okay.
Yes.
It have some size. This have some length L. So this give you something like e to the minus ml, right? So it looks like you are saying you are puzzled by on this size there's some particle of size m, and then but then on this state, on this future state, there's no particle insertion. So it looks like the energy is not conserved, right? So that's a puzzle. Okay. So first statement, on this geometry, if you measure the energy on these two
I had a
sides.
Lorentzian picture in mind, but
Yeah, this is the Lorentzian. Yeah. So if you measure the energy, you find the boundary energy is constant. At the boundary, this particle inserted, this describes when you insert this particle, O, this red particle, it has certain component to be an identity component. This C number, this certain component.
Sorry.
Sorry, maybe let me finish. This C is some random number. And in this ensemble average result, this wormhole is giving you this average of the C. Okay. So this is, so in other words, even though in this box geometry looks like you have a particle present, but this actually describing a state where the particle insertion does not increase in energy.
okay.
If so this operator can also have some you can also write as another operator which have a vanishing trace, and those component does not contribute to this wormhole. Those do not fall into the wormhole, but there could be some component where the operator does not create any energy excitations, but still non-trivial, give you some non-zero wormhole effect. That's the point.
Okay, thank you.
Yeah. Sorry, is that a question? Okay. Right. Okay. There's two more slides, but I think it's already running very late. So thank you.
If I can say, if you want to, please show your concluding slides or something, go ahead. I think we have interrupted you.
Okay. I didn't prepare conclusion slides, but there's two more slides. One is calculating. So previously we're calculating the probability of hitting a firewall, that's t²/2. But similarly, you can analyze the probability of after emitting a baby universe still remains smooth. There's actually no mapping class group issue, because you can show that if you after mapping class group, it goes to always map to an offshore state. And so it's just an honest integral of a dA from 0 to t, where the twist is from 0 to a. So that gives you the same answer as the probability of a firewall. And then it's an interesting phenomenon that when t is order reach e to the s, both become 1/2, kind of consistent with the Susskind conjecture. Although there may be more baby universe emission that contribute to this process. And the last slide is talking about the unitarity. It's a different, it's a boundary unitarity. So the unitarity requires the whole genus genus 1 wormhole contribution to be time independent. But in here, we are saying that the probability of hitting a firewall smooth grows with time from the wormhole correction. So that's seems not consistent with that the patching function itself to be time independent. But actually, there's an additional negative piece that's if you're calculating the patching function, it cancels. But the negative piece have a smooth horizon, and it actually cancels with the disk probability. So original disk just have normalized probability, But then this negative piece will cancel the disk probability. And so you can think about this wormhole effect as borrowing the disk probability to spread over the firewall and smooth components. And the negative piece can be thought as a quantum interference effect. And that's it. Thank you.
Thank you very much, Zhenbin, for a wonderful talk. Let's all unmute and applaud. Do we have questions? More questions? We have many questions. I think it's quite late there for Zhenbin. But maybe one or two urgent questions, if you can accommodate.
Just very quick clarifying question. Zhenbin, is this geometry an on-shell geometry, or is it that you? I mean, since you're doing the modular integral, I know that it's
right.
the path integral, but is there also an on-shell?
Yeah. So right. It's on-shell with respect to the Schwarzschild mode.
Okay.
For fixed A and S, and the A and S are their mode.
Exactly.
So maybe I can ask very quickly. You started your talk by asking whether typical states had firewalls. And sorry, what is the answer to that question with 50% probability? Sorry, what is your answer to that question?
Right. So the answer is there's odd one probability to have a firewall. So we consider one baby universe emission. That already give you odd one probability. But we didn't analyzing like a 2 baby universe, 3 baby universe, etc. So we cannot really answer like if the t is bigger than e to the s, what the probability becomes. But our current calculation seems consistent with a 50% chance. So at least there's odd one. So you can trust our answer. If t is like I don't know 1/10 of e to the s, then there's like a I don't know 1% chance to hit a firewall, which is already significant.
Yeah. Zhenbin, and maybe this is tied to Shiraz's question, but I didn't understand how time t is measured. Where do you start? For the eternal case, where do you start when you say this is the probability to emit a baby universe?
We start where this volume is small, the smallest, the volume of this.
So does that mean very, very far in the past?
No, that means at the time refraction.
Oh,
point.
I see. You start at
very into the past, the volume also large. If very large goes to 0 and going large, that's what the volume looks like.
So, sorry, so so you're saying start at the moment of time symmetry. Yeah. Thereafter, the probability to form this baby universe goes like t square e to the minus t, whatever.
Yeah.
Is that's the statement?
Yeah, that's right. That's right. Yeah.
Let's see. So is the statement that you have a probability to form a firewall, say with 50%, the statement if you have started after this moment of time symmetry?
Yes. Yeah.
Okay. I see.
That's what like Lenny's original argument.
Okay.
Exactly.
Okay. And then, as you said, if it's a black hole that forms from collapse, perhaps the moral is that just as the clock starts when the black hole forms, presumably, and you.
Well, yeah, forms are like forms a little bit like thermal times. Those are just treated as 0 in this time scale, where time is called e to the s. Yeah, so thermal time scale are just 0.
Sure. Okay, after things settle down, and then you say that there, as long as you're after this t of order e to the s, then you got a 50%. Is the statement that you have a 50% probability after time t of order e to the s to be in a firewall?
Okay, I wish to say that, but our calculation is not able to show it's a 50% because we only consider 1 baby universe emission. So that could be 2 baby universe and 3 baby universe. But our calculation consistent with that. We can only see the rigorous result we can see is that odd one probably to be the firewall.
Okay, thank you.
Okay, if there are no further questions, let's thank Zhenbin again for
okay. Thank you for great.
Thank you for the stimulating questions.
And thank you for answering the questions so patiently. Thank you.
Yeah, no problem. Yeah, those are good questions. So I think I should clarify those questions. I hope my answer satisfies
It was great.
Yeah, of course. Thanks.
Thank you.
Thanks a lot, Zhenbin. See you
Yeah,
soon.
no problem.
Bye.
See you.